Am I on time or am I on time? Whoa! Bro, looks like I'm on time today for once. How the hell did I manage to do that? Today I'm on time and yeah, we're gonna get started with Bitwise stuff. And Bitwise stuff is pretty amazing. It allows you to do a lot of stuff. I already started working on stuff here, but this is a DUB project, and I would prefer to actually use DMD project. Just my own shit, so. Goodbye, project. New file. We're gonna create a, paste. And then we're gonna save as. Actually, we need to make a directory for this. Nah, yeah, we'll be fine. Desktop, dtools, create new folder, call it fish bitwise or fish libs. Yeah, fish libs, guys. Or actually, just call it a fish common. Yeah, everybody wants to use fish common library, okay? Just call it fish common, okay? Hell yeah. Fish common is gonna be... Oh. Fish... bitwise .d enter. And so what this is basically a program that will set and get bits. See, I was looking at DUB and I was like, well, they have a system that does this, but I don't want to use their system. I want to make my own. And so we've effectively got that with this, which gets a bit. So if you have, for example, the input 16, or I think that's 16? Let me do the math in my brain cells. 16 would just be 1, 1. For example, let's just take 0f, for example. Control S. Shut up! Oh my god. And then get ourselves to that directory. CB... There's some other things I'll have to explain today too, since there are some new things I'm doing that have changed how I do things, kind of. And we'll change it for the future. LS. Alright, so we have... RM-RF... And why the fuck would you use a mouse, guys? I'm just saying. Why would you use a mouse when you could just type it all out yourself? LS. Beautiful. Now we're gonna go ahead and DMD. I actually want to run a time command on this to see the compile time. Bitwise. That's the times it took it to do that. I mean, not even really a second. Then we'll do our dot slash fish bitwise, which gives us 1. Now, if we write this out, for example, new. Let's say we have, what is it, an int? We have 32 bits in an int, right? So an int contains something like this. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. That's good enough. 0, 0, 0, 0, 0, 0, 0, 0, 0, and 0, 0, 0. This right here is effectively 1 byte. Just to give anybody who doesn't know shit about this topic an idea of what I'm talking about. Basically, this is a byte from here to here. So that's a byte. That's what you would say is a byte. It's 8 bits. So effectively, a byte is 8 bits. And this is effectively how file sizes work as well, if you don't know shit. I mean, this should be pretty basic. Like, you should know that your file is made of bytes, and that bytes are made of 8 bits. Now, in an int, which is 32 bits... Oh my god. Int 32 bits... we have basically created the number 16 as 0f, or 0x0f, which is a hexadecimal for essentially this number, 000 Let's think, what was it again? It's basically this. That's effectively what we've created. That should be 16. Actually, I'm pretty sure if you... Let me refigure that out, because my brain is not currently turned on. It's been a while since I did this. 1, 2, 3, 4. Actually, it'd be better to increment. That's 4. Actually, 1, 2, that's 3, 4, 5. And then I have this. 6, 7, 8, 9, 10, 11. Oh, actually, that's not counting correctly. God damn it. Now I'm just gonna make a binary table just to make this easier. Good God. Well, I mean, it's okay. People don't usually work with binary, so, but when we start working with bitwise stuff, we have to start working with binary. So that would be like 0, 1. Next one is this one, 2, 3, 4, 5, 6. Wait, we skipped one. There should be one like this. Alright, so then, of course, boom. And this will be pretty useful for just figuring shit out later. Just to have this in case. There's a very simple pattern here. Every time you have a new bit, you add a bit. And that's the interesting part. That's why it's important. Actually, that wouldn't be that. It would be... Yes, 1100, then 1101, then 1110, 1111. And that's inside of your half byte, or whatever the fuck this is called. And if we do tab 1, tab 2, tab 3, tab 4, tab 5, tab 6, 7. Actually, this would start at 0 because that's how it is. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, that's not, bro, 13, 14, and then 15, which corresponds to, in hexadecimal, just making sure it's indenting correctly, 0x, 0f. Should be that in hexadecimal. But let's start from the beginning. So we have 0x00, we have 0x01, 0x02, 0x03, 0x04, 0x05, and for the first 10 numbers, you'll notice that this is basically just regular numbers with a 0 in front of it. 0x0 in front of it, effectively. But this is more than that. It is a way more compact way of storing numbers. So, storing numeric values inside of a decimal number, which is the system we typically use for math, is like shitty, because why would we do such a thing? This is way easier to read. Actually, it wouldn't be 11. It'd be A. That's where things get weird. But it's also not that, or technically I think it stops at 1, 0, because you don't even increment until after that. It becomes 0A, 0B, C, which should be 12, and that is correct. That's the one I do know. C3 is return in 86, or times 86, so that's what I remember. Or just the guy was talking about that. And then 0x0e, which then, that's how you can recognize these. So if you took this and made it simpler, you would just put all the things into that. And since we take 0x0f, we're effectively taking 15, which is, the first position in 15 is a 1. However, 16 is where things get interesting, because now we need a second set of bits for this, and that's when we start to look at it being a 0 again. Because, remember, they alternate all the way up, so as you can see, they're alternating all the way up in this pattern, and then here we have 16, which is 0x0, or 1, 0. That's 16. And now, semicolon at the end, bro. Ain't no way I'm just that used to it, but anyway. That's now this. And we could technically take this and represent that number in hexadecimal as well, just to make sure everybody understands the concept of this, but if we took it and represented it in hexadecimal, it would look something more like this. Inside of a hex editor, obviously, you'd have 0, 0, or something like this. Yeah, the pattern here is very noticeable. So you'll see that on both of these rows. For example, here, on this row, it's going to do 2 between each one. On this row, it does 4, and then on this one, it does 8. Which you can, I mean, who knows how this pattern works? I'm sure there's some math genius out there who could tell me exactly why this pattern exists. But, I suppose it's got something to do with it incrementing. I mean, it's definitely related, or correlated. But, to continue, effectively, we have a byte here. In this number, that's a byte, which is, can also be represented like, 0000, which is also technically, let me go down and do that so that way it's separate. 0000, which is effectively also a byte. So there's that. And if I had 1, 2, 3, 4, that's still 8 bits. It's just an easier way of representing it. And this is how it will look in a hex editor. But now we have inside that first position, which is like, or inside the second position, we'll actually have that 1, which remember is represented as 0x10, or in this case like that. And so if we do it here, so this would be your 32 bits right there. So int stores 32 bits. Now, yes, we can use doubles or longs to create even bigger amounts of binary bits. Of course, for this case, I'm using ints just because I need a quick way of setting it up to demonstrate it. But I want to be able to use any number with this, which is kind of a key thing that I need, because that will be useful for making this a very standardizable library that I'm going to make. Basically, it will contain a bunch of different bitwise functions, and that will allow me to build things off of bitwise operation. Since for me, bitwise is easier to understand than a lot of things, so. But this basically should point to that. Now, if we took another one and we made a 0, 0, 0, 0, 0, 0, 0, 0, and 0f. Actually, that's not how that would look. That'd be a 1 in the other place. What am I saying? Boom. So if we're checking the 1's place, or the first... If we're checking that first area, which I'm pretty sure is called 2's actually. But if we're checking there, we should expect to see 1, but then we should expect 0 here. So let's go ahead and try out 16, since now I have this to kind of represent exactly what I'm saying. And I'm going to save this just so I have an example. Plain text document right there. Boom. Nice. So we're going to change this to 0x10, which should be 16. And 0, as expected. So if we change the position to be the second position, we should get a 1. So in this case, we're checking the first position, but here, if we check the second position, it should give us a, it's giving me 0 in that case as well. But what is the value of the number? And it doesn't even write the input. Oh wait, it just writes that. Okay. Well, let's write ln of the input, just so I have that to keep track of it. Something else you'll notice is that now inside of my programs, I'm importing things inside of my functions, which is a way more effective way of doing things. Although you're going to have to do that for every function. And it might make the compile times longer. I'm pretty sure it could potentially do that. 16 should not return 0. So what is going on here exactly? So this is an AND operation. This is a shift right operation. And we're taking input and we're shifting it right by position. And then, so for example, well, yes, and then we're doing an and 1 on it. And, which, fucking basketball, bro. We're doing an and 1 on that shit. Yes. So we're shifting it right in this case. So like, if we were to work through this problem, we would take input and we would just do that. So let's just do, for example, input and then 2. Shift right by 2, just to see what exactly that's doing. Four. Which I don't believe is correct, because in the case of 0x, 0f, it shouldn't be doing that, where it gives you 4. That's a quite a strange thing, but if we do the full thing... Actually, we aren't even writing the output of this. Well, hold on. That one gives you 0. Though the position might be that and. If we say this is position, does that work? Oh, wait. Alright, yes, this. Zero. And, well, what does input and that do? Because that is technically an AND operator, isn't it? For bitwise ANDs. 0. Well, yeah, it's comparing it to 1. Obviously, we don't have that. But that returns 4, and this is checking it against the number 1. So in that case, we're checking 4. We're checking if 4 and 1 are true, basically, which is going to return whether that's a Boolean. Effectively, what we're working with is just Boolean. There is not really much to this. It's just Boolean. That's why we get a 1 or a 0 on a normal return. Like in that first case, we got a... what was it? Fucking 1. That's why every time it fails, it gives a 0, because it's not actually giving anything. It's giving you a Boolean. So, yeah, expect Boolean, but... Which is the smallest number. Effectively, if we took Boolean and put it in here somewhere, Boolean is literally just a single bit. So, that is why it's bitwise. Although, I don't use Boolean very much. Although, I'm pretty sure with this we'll be using Boolean plenty. So you shift your input by your position? Or do you check what is at that position? I mean, this checks the position, right? If we switch this, and we check what's at position 2... Still don't understand. Well, we're making a code that checks the position. For example, we just need to find out if there's something at that binary position. Like, for example, we have the number 16, which should effectively be this. Or if we represent it in binary, it'd be the well, it'd look more like this: 0, 0, 0, 0, 0, 0. Well, I need the shift position to set that. Oh wait, maybe we don't need to do that. You might be onto something, but I'm gonna check in a second. Should look like this for 16. The other one should look like. Oh wait, I already did that, didn't I? But we should have... Well, shifting it sets the value of input, or no? No, wait, the reason you need a shift position, right? So when you do a shift position, that gives you the value 4, right? Which is to say that we've shifted it. And then we're going to test that. So like if we take input, we're going to shift it by position. For example, if we shift it by 2, for example, that also has some questions for me. Because that's not a... Let's set this to 0x0 2, just so it's easier for me to read. Which should return 0. But yeah, so basically, this will return 4 for whatever reason. Now, when we had 0x0f, it was working perfectly for whatever reason. Gave 3, and then we check it at, it should be checked at 1? Or checking it at 2 gives that, so it returns a 2. That gives you a 1. I mean, all 4 numbers in that half byte should be correct. We want to check the position. Maybe it's because this is I don't know. Also, what we should do is change up the what's it called? Change this up to make it a... Oh, wait. I know why it's returning 0. It's doing it correct. So, let's go ahead and relook at this example. So, here I have... We were checking this one. Returned 0. That makes sense. Because it checked 2 and returned 0. We need to check 5. But you'd expect the value at position 2. I mean, we're working with weird numbers here. 15 and 16 are weird. Let's go ahead and redo this shit. Do 0x05. Technically, we can just work with 5. Since I don't really need those anymore to check it, because I know it's going to work if I put in 5. Oh, return to 0? Oh, right, because it's doing that shit now. And 1. Returns 0. What number is it checking? Oh god. Oh. That's not correct. Alright, let's do that now. Five right there. Or actually, yeah, that would be good. Zero. Why? Why would such a thing occur? Oh, because we have 15 again. How did we get to 15 again? I thought we were checking 1. Oops, that's me being very dumb today. What the hell-y? Is there a write raw option to like write out the raw number into the terminal? Check at position 4. There's something at position 4. But what does that mean? That means that it checks and does this one. Oh my god. Who would have known it would be so hard to do such thing as this? That's why they made this for. Haha! Wow, look at that. Checked 4, returned 1. And that's for the number 16. 16, right? Or 0x0 or 10. But that shouldn't have done that. That's weird. Because that's 0x01. 0. Input to 5 gave us 0. And the input... let's import... Let's open up a struct. And then do a raw write. So, what is it? Standard.file? Do I need standard.file for raw write? Let me check. File.rawwrite and dlang. Method, okay. Create your file as usual. Oh, you can just use the... We'll put in the struct file. It should just give us everything we need. Or whatever file even is. It's like probably a method or something. We'll check if that compiles in a bit. Well, to look like a pro, you want to do auto file equals, or actually, if you want to look even better, debug log equals, actually, let's just call it log, because I like log better. Even though that's a standard.math function. I don't have the standard.math even in here. Why would I use standard.math right now? We don't need that. Log equals, what do you do? File. And then you put your file name, which is, debug. And then you have your, append. Right? Or actually just give it A. I'm pretty sure it's capital A though. No, it's just regular A. And technically it's A plus if you want append plus, which writes at the end of the file, or append, well actually it also can make a file. Or it's plus A. It's one of those two. We'll see if it compiles. And then you do log.raw right. But make that right capitalized. And then, output equals get bit. Which no longer needs a brackets like or parentheses like that. And you can do write ln for get bit or the output, just so I can see it, and then we can get a binary file of it. To do this correctly, we'll do a .bin to store it in. That way I can just go straight into the hex editor with that. Raw write needs, what was it again? It needed something. Right, I think it needs some kind of access. Ooh, documentation. So boom, then you would do that. Oh. Then you do your file.close at the end, obviously. So we'll just do log.close, but it doesn't really, I think it does explain how to do it. Let's just, we'll check that in a second. Pretty sure it's like that. Yeah, it is like that. Alright, so we're making good progress. Oh. Okay. Oh, right, yeah, the actual name of the file should be stored in the struct log or whatever this is. The, it is a struct, because it doesn't have a new. Or, unless it does have new, then it's a class. I mean, it certainly acts like a class, because it has functions that are associated with it. But yeah, you would do log.rawWrite, and then you put in whatever you're going to write in there, which in our case is going to just be the output in a binary form. So let's go ahead and run this again. And it doesn't know what output is, which output is right here. So that should be an int. And you do it inside of this scope because this scope allows you to contain it. Eventually you could technically take this and make this into a function. A void function of some kind. If you were going to recall it a bunch of times and use it in a bunch of different places. I mean, it is valid to do such a thing. Int. Okay. Cast to string, or actually cast ubyte, or no, don't do that. Cast string oh, you sure about this? Okay, what is it? How do I do it in the one example? Actually, what are they? They're doing a string in a raw, right? Where's the example at? Should be in here. Oh god. That's not the one I'm looking for. That's so empty, bro. I didn't even realize how far I got in that project after I gave up on it. That's sad. What a deprecated project. It will never exist again. Any of these ones will have it. Alright, here we go. So then we have right is in here somewhere. Where is raw right at? I thought we did raw right in this one. Right raw. Raw right. Cast return results. Oh god. Bro, this is the one that had immutability issues. It didn't even have modules yet? I'm sure that the modules are actually handled in these. It was in the next one, wasn't it? So let's just go back. Let's go up a layer. In here? Maybe it's in this file.d. Alright, perfect. So it writes a word.word. What the fuck is a word.word? I know the word.word comes from somewhere else. Alright, so in this case, we just take that. I think it does it by the bits of it. Oh, wait a second. So yeah, in this one we break it down into car. We break a string to car, and then well, car array, and then it should just be in here. Let's check. Probably in the structs. Yes, and word is just an int for the word position, so that's for the concurrency part of it. And then the ushort array. So raw right expects not that. And it wants an array. So, I mean, the only way I could get an array is by creating something that works the first time, and I don't want to do that, so, I mean... unless we can cast to a string the output, or a wcar array to the output, or something. Like, there's really no way to use file raw right to our advantage to leverage something I can actually read for the binary values. Unless I could write it as a binary value inside of the terminal, but I have no idea how I'd do that. To make it easier to figure out what the hell is going on with this number and why. I expect it to be at 5, which is what I expect, is that it's going to be at 5. But it's only at 4. We'll just get rid of this. Maybe not. Brain cells. This will be fine. Okay. Control and save. So yeah, we expect it to be 4, or check 4, and it returns 0, but it's returning 1. Zero, 1, and 16. Am I wrong about how that works? Is this is not 16, I'm guessing? I mean, you would have had to increment 16 times to get there if you did it by 1. Unless this is wrong. Unless I'm missing multiple numbers? But I don't think that's the case. I think this is correct. This is definitely... So why is it that it's returning not what I expect? Wait. No, that would be in the first 2. Right. So this is the first byte, which is represented here. This is the second byte, which is represented here. Third byte here. Fourth byte here. This shouldn't look like that. I mean, that's kind of wrong already. For 32 bits, you would only have this much. Boom. So you would expect that... I mean, if you're checking 1, it should be 0. Am I checking? What am I checking? I should be checking 1. We're checking number 4. If the position is 4... Is that a number? That returns 1. So it's at position... Well, it's at position 0. Wait! Oh! I just realized. What if we check position 0? For example, we check 0 at the 0 position. What if the fucking number starts at 0? My brain cells might have kicked in for once. 16. That's not right. Wait. Yeah. What? What? Hold on. There would be no value if there is nothing at 0. So if you AND it with 0, or if you go to 0 and you check for a 1 at that bit, then how do you... What the... What does that mean? I don't understand. Like, we put 0 in, expects 0. Or expects 1 and it doesn't find it. But if we put a 1 in... If we put a 1 in, it should find a 1 at the position of 0. Aha! Maybe that's what it is. So at position 0... Yeah. This is not position 1, okay? So let's go ahead and explain further what we've just realized is that, okay, let's go ahead and do our, Alright, let's just do half of what we're doing. So half of the full number, right? This is position 0. Not position 1. I think this is the case because it would make sense that it starts at 0, but not only would it make sense that it starts at 0, but our results have also been showing that if you check for 0 and it's at 0, it's 0, and then if you... Because it's checking for 1. When we put 1 here, it returned 1. Can we make that Boolean so I can determine if it's true or false? I mean, I could do that, but... These are for 32-bit values, technically. I'll make some for different values. So I'll say set it for get 32-bit and then 16 and 8-bit values too. That way it can be very memory usable. Or just make one that you can just set what the value's gonna be or what to return at the end. I'll figure out how to do this in some way. I'm not sure yet. That way we can create a program that handles these numbers and then allows the user to, well, actually allows me to create a runtime, basically, that emulates a very strange machine that I've contrived in my brain. Somehow, eventually, it'll be the end goal with this project, I think. Fish Bitwise library for Fish OS on the Fish emulator. Or Fish emulator will be used to create such great things. It'll be like Java, but better. That's what the plan is. So yeah, it works, but it's weird. So like if you want to check what's at the first bit, for example in 0f, it should return a 1. Which is true. That's perfect. So it works. Kind of. Because it needs to be position +1 to make it simple. But if you're not stupid, you can understand that what we could actually do is write a for loop, right? So let's do a for each loop, I mean, because, bro, the for each loop just fucking is so clean. I don't know how you get a for each, or anything better than this, but for each loop always is 0 to 31, which should give us all of the values inside of an int. No, don't do that. For each loop is the cleanest loop I've ever seen, though. I'm telling you all now. Boom. And then it's going to append that to an int array called output. But that needs to be on the outside. So get rid of that and append it here. And then int array is dynamic. Output, semicolon, save. And then we'll write the line for output, but we'll write each output. So we'll do, instead of write line, we'll just do write, and then, why do we even include file, write ln? Boom, like so. Just get rid of this, because I don't really need to know what that is anymore. And then we'll do a for each for the value of output, which means for every index, let's actually switch that so it's easier for beginners who are more beginner than I am. Index, for each index of output, put that there, tab, then enter on both of these just to make it look pretty. Yeah, just to make it look oh, one last thing. Boom. That's the loop that will create a 32-bit number. Oh god. Why did that have to look so bad? It should just write the line index. Okay, hold on. That's a bit unfortunate that I did that. Did I do something else? Okay, let's go ahead and oh, what did I do this time? What did I do for this time? Oh, I didn't check each one against bro, I just appended a bunch of ones. Alright, let's try this again. There we go. What the fuck is that? Is it appending in reverse? That's my first question. Is this appending in reverse? I think it is. I'm gonna be honest with you. That's definitely appending in reverse. I think we can do this by going from 31 to 0. Which should create the loop we're looking for. How the fuck does that not work? Okay. Well. Or we would do 0 to 31 and have a different counter. Or we would write them in reverse, which is an option. Or reiterate the indexes in reverse. Don't do that. Those are all dumb options. Instead of this, we'll just have a... Is there technically a bit size? Because that would also make the array more efficient. So yeah, instead of doing that, let's just do... Technically, yeah, you could do a for each loop for this and just have nothing in this one and just do for each 0 to 31. I think it's more effective to do a for and then do an int I equals 0 to make it work inside of a function. Then get rid of all that. I is less than 31, which it starts at 0, and then minus minus I, and switch that around so it's greater than 0 and starts at 31, which should give us the same effects as appending to that specific, and instead of appending, let's set that to equals the index of I. Then we can do our for each, which should give us a reverse output. Oh, for array length of 0. And it's dynamic. Oh, right. We expect 31 bits, though. No, we expect 32. That worked. Which didn't work? What the hell did it do this time? So the reason that didn't work is because it's got a 32-bit version of it. Did we start from there? We should be appending if we're doing it like this. Let's append. Let's do this correctly. I think that will work better. Confuse. Cannot append int to type. Yeah, because it's not dynamic. Right, because it wants to... Yeah, that makes sense. That gave us the correct output, except... Yeah, it is the correct... No. That's not the correct output. What the fuck is that? Give it 32. Or we could just do dot length. What the fuck? No, we can't do a dot length either. So that just creates an extra one in the front. I'm trying to understand what's going on right now. So we're appending that. So I equals 31. It takes the input and it uses the I to get that. For example, when it goes to... Why would it be taking... When we start at this value... 31, right? We're starting at 31. It should append to 0 as the first thing it does. So, starting at 31, it appends to 0. Boom. It goes, oh, there's a value at here that is 0. But then it's also checking at the other value, and it's saying, this is a 32. Oh, and technically, once we've done this, we can actually write an output into a binary file. But that should be doing a, more than that. I mean, you could see earlier we got 4 ones out of it. How many numbers do we have? That does not look right, because I feel like that's some more numbers there. Where's that? This one. This one we had 4, 8... I think I can see another 8. Yeah, it's definitely 32. Let's go ahead and get an idea of what I is doing before it. Write ln. And then we'll do the, this. We'll do I, comma, space, Control V, semicolon. I think that will work. I don't know. Figure that out. Apparently it does work. I've never done that before. Ah, it's not going to 0. That's what it was. That was so easy to figure out. All I had to do was do one right line. What the fuck? Stop doing that, bro. You know, I might just have to remove that from that screen. Boom. It gets all of the numbers now. So that gets us our 32-bit array, basically. So this creates a new function for us called get bits. Gets us a 32-bit number. Wow. Technically, you can also set them too. For example, if I want to set a bit, let's say I want to set that one specifically to 1, or flip this one to 1. There's a way of doing that, which I believe we'll just do it in an inverse of how we do this. So we'll say that the... hold off on that until I actually have a pretty good idea. But yes, we now have a new function, which is going to be a array. So we'll call it a int array for goat bit noise. Get bit noise? Get bit noise. Bro, goat bit noise? What the hell? Get bit noise. Yes, very nice. Bro, what the fuck are these Google AIs doing in translating everybody's shit in chat, bro? Google AI, bro, it's fucking terrifying. It's slowly turning all of chat's messages into translations which nobody asked for. Anyway. Get bit looks pretty good. Get bits, which is gonna take nothing because it's just get bits. I'm thinking when I make this as a full library of something. Google Slapify? Yeah. Bro, YouTube is owned by Google, bro. And then we don't need to write the index of these, I guess. We could just return a... Instead of doing that, we'll just return... Because that's not a hard thing to set up. That I could just return as a... function, as a array. Return the output. So it's going to create an int array here. Boom. So that returns that. And then we can take an output from there. Boom. And that should be the same thing as what we've done. So for example, if we put in our input number, which is going to be the input, int input. So this is for 32 numbers, or for 32 digit numbers. Or 32 digit numbers? Bro, 32 bit numbers. So I guess Fish OS is going to be 32-bit, or the Fish emulator will be a 32-bit emulator that handles Fish emulation. Fish emulation. What have we really gotten to, guys? But that will check every value in that input. So if I put in, if I now do get bits, write ln, equals get bits. Or no, why would I do that? Get bits. And then we would put another set and then put input. Just to test it out. Which should just give us a array version of that. Which isn't really clean and I don't like that. But right. Ritlin. Bro, what are we doing? Right, Ellen. Oh, right, it's in this function. Where's it at? Right, Ellen. Get rid of that. We don't need that. That's slop right there. Boom. Look how good my code is so far, guys. What do you all think? My code's impressive? Gives us our array. And now we have an array we can work on, which makes things a lot easier if you want to use an array. Now, technically, it should return a byte array because you shouldn't be using, well, bit array. So let's go ahead and look at the data types. Delaying data types. There's byte, ubyte, which is what the smallest one you can work with technically is boolite, or ubyte. Sorry, I was thinking of bool. So I think we should just cast a bool array. I don't know if this is gonna work or not. It's gonna be like, can't do that, I'm sorry. But if I cast it, it will do anything I tell it to. Cast bool array output. This is the most Giga Chad thing to do of all time, is to tell it to make a fucking bool array from a... It accepts it. Bro, it also gives that. Oh god. Okay, so now what we're gonna do is oh god. How many is that? Shit, bro, that's a lot more than I expected to return. Maybe we shouldn't cast it to a bool. Cast it to a U-car is what I was about to say, but cast it to a U-byte. Oh god, that's even worse. What the hell kind of output is that? Creates a U-byte array, and then it stores 0, 1, 0, 0, 0, 1, 0, 0. Oh my god, bro. Okay, so that's not gonna give us what we're looking for, but that's because we're trying to cast that. But we should be trying to cast it as a bool. You can make game find true on this text. Ooh. That's not what we're trying to do, though. We're not trying to make a huge mess like this. True, false, false, false. Doing a U-byte did that. Doing an int array is normal looking. Maybe it's because we're casting it? What if it's just that we were casting it? But it's gonna say, you can't do that because these are weird. Cast bool to int, it'll go 0 or 1. Let's see what this does. Yeah, oh, wait a second. Because I guess what we were doing was, that works, but it also doesn't give us the expected output, which is something like this. That's because of how the data types work, or data types work. So basically, every array is allocating one of that size. For example, the original array here is going to cast, or is going to allocate 4 zeros, or 4 bytes of 0, and Boolean is working on the lowest level, which is ubyte. So technically, Boolean and ubyte. Boolean is not bitwise, and ubyte also. So when it does that, it also places the value of that at the front of each of these. So basically in this, you have one int for the value of 1. So that's how the int works, basically. It stores that first number like that, which is to say that arrays allocate data. For example, if you wanted to allocate data, you could literally do an array where you do int output equals new int array, and then give it a number inside there. That will actually allocate an array buffer, kind of. Well, literally is an array buffer. Very interesting stuff. But that's for memory allocation and stuff like that. Literally pretty low level stuff. At a high level. Abstract level. So yeah, the reason this isn't working is because it's doing it like this. But we want to cast it in here, so that way we don't have to do all of that. So what we'll do is instead of doing an int for this, we could just do a ubyte, or we cast that to a ubyte before it even gets there. So cast, and I'm a little bit worried this will have the same results or something worse, but you only get better at doing things by doing them. And I'm expecting... interesting. Ubyte array there. Okay, that worked. And the reason we want to use a ubyte array is because it's the smallest data type we can get to hold these numbers. Other than potentially Boolean, which is literally supposed to be true or false. Although I'm pretty sure it's stored as a ubyte. This one. That gave us our results. And so now, see if bool, like, bool versus ubyte dealing. If we look at C, it will be like wrong because there's a bunch of things to see. True or false. Implicitly converted from integer values, preventing accidental Boolean usage or arbitrary numbers. Or of arbitrary numbers. Oh, okay. Creating my own numbers. Bro, that's crazy. Creating my own numbers. Yeah, let's see the performance impact of bool versus ubyte, bro. Let's try to get the high-speed program of all time. In raw execution for arithmetic or logical operations on modern CPUs, as both occupy 1 byte and are subject to the same hardware constraints. However, their performance characteristics diverge in memory bandwidth vectorization and type safety. I don't really want to learn all that, but memory bandwidth and cache efficiency. Primary performance advantages of bool over or ubyte over larger integer types like int arises from large arrays or structs. cache utilization, since both types are 8-bit arrays, consume 1/4 of the memory of int arrays, which I've already discussed on 32/64-bit systems. This allows 4 times more elements to be fit in the CPU cache, significantly reducing size or reducing cache misses and memory bandwidth pressure during iteration. When used in structs, bool and ubyte allow for tighter packing. Placing 4 ubyte or bool fields next to each other avoids the padding holes that would occur if they were larger types without careful alignment, leading to smaller overall struct sizes. Better performance when these arrays of structs are processed. Wow, vectorization safety. Compilers like LDC can often vectorize operations on ubyte arrays more aggressively than bool arrays. I mean, I like ubyte. I'm a big fan of ubyte. When interfacing with C APIs. Look at this. uint8_t? Like, oh my god, bro. Like, that's fucking cringe. Who wants to write that shit? Just fucking put ubyte. Like, what is that? C data types versus D-lang. Bro, if you use C or C++, prepare to be embarrassed because you have like 300 data types that you don't need. Like long, bro. What the fuck is a long? List data types.
Well, you have your int, and you have your, and you have your other things, and,
Primitive types. Char, short, int, long. Write a car pointer, bruh. Car pointer, bro. Derived. This isn't even the full list. There is a full list. I think I have a screenshot of it. But C, bro, C and C++ are just killing me inside. I'm like, why the hell would you make languages this shitty? Like, C++ is only shitty because C was shitty, and then now they're both shitty together. They're like the shitty pair of languages that wants to be shitty and like extra. D-lang is where it's at, I think. But yes, we got our array of these, which allocates ubytes. The most smallest amount of data possible to store, apparently. But I want to store bits. Is that an option? Is there like a bit array? Can I make a bit array option? Like D-lang bit array. Not a built-in primitive type. Instead, the standard library provides standard bit manip bit array. Oh, wait. Yeah, but that's somebody else's work. Dynamic array of bits allowing individual access. Standard bitwise operations. Oh, and there's also OR, by the way. C was made in like the 60s. Yeah, but it's trying to be a modern language still. Yes, it could have been made in the 60s, but it's still being used in the modern era. And it technically started after, like, B-lang, bro. You might not know this, but B-lang came first, which came after APL. Or, well, around the same time. B-lang. The B family, or B primarily refers to the B programming language, which is basically just this. 1969 by Ken Thompson and Dennis Ritchie. Acted as the direct predecessor to the C programming language. Lacked data types, treating all data as the underlying machine's natural memory word. Introduced two address assignment. So when did C come around? Oh my god, I am not a robot. How dare you? 72. At Bell Labs, but also by Dennis Ritchie, who also worked on C++. Oh wait, no. But it was made at Bell Labs as well. Pretty sure of that. But yeah, all that comes from Beeling, apparently. But what came before Beeling? I'm pretty sure it was APL. Though it sees niche use on GCOS mainframes. That's why I want to get one of those. And embedded systems. Oh, wow. Very interesting. But, Beeling compiler. Can we interrupt this in my D code, bro? Oh, wait, what? Damn, there's actually a Beeling? Bro, it's still around to this day. It lives on in somebody's GitHub repository. No, I'm not doing that. I quit GitHub. I'm retired from GitHub at this time. This is very good news, though. Very good stuff indeed. So we got our right line bits get input. So for example, if we have this, input 2, let's just do 2 numbers. Let's see what happens if I mean, it should work if we do. C3 is my favorite, so let's put that in there. Ah, does work very well. Returns the expected results. Now, that's going to be get bit array. And then ubyte, because that's the most efficient way of doing that, is to store return, and then we want to return. Why is it in that? We could do return cast ubyte and then bin. It should work. That will be the most effective way of doing it. I'm sure. All right, get bits, get bit array. Because get bits and get bit array are going to be 2 different things, I think. I think get bits will just return a entire integer of the bits. Yeah, it still works. So then if we do get bit, then we should be able to do get bit, just do input, well, then input and I. Oh wait, this means we don't even have to cast these, because get bit returns ubyte, so how would that even need to be casted? That should now work perfectly without requiring any casting inside of this function, the for loop, which would significantly increase performance because... Let's try it with the cast and without the cast there. I want to see the timing on that. So time dot slash bitwise. The reason I want to try that is because I'm actually unsure about the timings on such things. Like, that took 0.2 seconds, but if we had the cast in there, surely it takes a bit longer. cast U-byte, since, like, what if we don't know what that is, right? Then we would cast the U-byte. So that's the time for that. Then compile time, I feel like, was longer. When we didn't have that in there, the compile time was, yeah, it was like 2 seconds less. Or 2 of whatever the fuck those are seconds. Like, barely much of a difference, but that could just be a bunch of other factors too. However, the runtime, I feel like, there's still really no difference noticeably. I mean, it's still a performant program regardless of this cast U-byte. I think it didn't really make a difference. I think that's... There's also something else to note, which is that with these, like, there's the garbage collector, right? The garbage collector is like a scary thing in D-Lang. Let me go ahead and draw an image to explain the garbage collector. So new, there's a garbage collector, right? So the garbage collector, he is like this. And he live in your RAM, bro. So this is the garbage collector. We call him GC, or garbage collector, right? And so you have a variable. And garbage collector will grab this variable. Yeah, I would have optimized. Yeah, I'm sure. Bro, that scared me. So yeah, garbage collector grabs that and then he throws it away, right? So throws this shit away. Throws it away. Boom. He garbage collected. Now that's pretty scary because, you know, what if I want to say, for example, garbage collector, I want you to throw it away, but do it later. All right, so that's what I want to have is like a garbage collector that I want to basically tell the garbage collector to throw it away. You know, see, like garbage collector can be lazy, right? Like, so let's say we have that var right here, and he just is like, I'll do later. And he just ignores that one. So I want to create something called var destroy. Right? Like this. And he's like, oh, get it. So that's my explanation. I used the whiteboard today because that was amazing. I hope you all enjoyed my great depictions of the garbage collector doing his job. So garbage collector is amazing, right? Now, here's where classes kind of fall into that. I think classes allows you to actually deconstruct them. And so we're going to refer to the D-Lang book, the Book of Jesus Christ. Some people have asked me for the Book of Jesus Christ, and I'll provide this at this time. Hold on, let me get 5 seconds to go find the programming in D-Lang book, which exists. This is the ultimate book. The D-Lang book, pirate software moment. I'll provide this at this time. And next up is to go to my documents and pull up such book so we can all read the Book of Jesus Christ together. Hold on, looking like a real professional here on the Book of Jesus Christ. Oh! You didn't expect me to figure out how to make this thing work, but I did. And that's the Book of Jesus Christ. Now it's time for me to find what I'm looking for. And that's going to be hidden from me. It's going to be very far away. It's going to be in the... what are we looking for again? We're looking for deconstructor. What? How do you mean there's no deconstructor? There's a constructor. Deconstruction. Next. Operator overloading? Wait, that's a thing? Bro, I thought in the symposium they said they wouldn't have that. Because it's called like, oh, what's it called? In C++, it's called a destructor. God damn it. But in operator overloading, there's well, operating overloading is called ad hoc polymorphism. Operator ad hoc polymorphism, bro. Which is like, that sounds pretty... I didn't realize there is actually operator overloading. I don't know what that means, really, other than it means you can, like, build a fucking thing that's just a bunch of fucking... it's like a plus with a bunch... You know that fucking Linux meme where it's like, what's it look like? Linux bash meme. Let me find it. Bro, where's the one where it's like a bunch of... I'm pretty sure you all know what I'm talking about. But in the terminal, you can do some weird shit, and it's like... a bunch of fucking operators together with a pipe and a bunch of other shit. And it's just like, what the fuck does it even do? It doesn't even mean anything to me. It's like a bunch of... That's basically what operator overloading is. Classes, inheritance, destroy and scoped. I guess destroy to execute the destructor. Ooh. But yeah, that'd be on a class, right? So you'd make a new class for it. I mean, I suppose that it'd be efficient to let the garbage collector handle this, but let the garbage collector handle it, I'm sure. I'm sure they know what they're doing and made a good garbage collector, and we don't need to worry. But yes, you could technically make your own rules for the garbage collector and shit like that. You can also specify, like, at no GC to, like, get rid of the garbage collector. I'm gonna have to watch more videos today, but, I mean, they should be pretty easy to do. To learn a bit more. If I can get time for that. Lifetimes and fundamental operations. This sounds like something we need to learn. Let's go ahead and scroll up. So lifetime of a parameter depends on its qualifiers. Oh, these are important. This is important for the garbage collector, which I need to understand the garbage collector, since when we go to write fish OS, the real thing, and not just the fish library where we're using Bitwise to make my own binary library where I can do anything with binary and stuff, and create some kind of weird pseudo language that runs on top of dlang. I don't know. Expression-based contracts? Contract programming. Wait, this is that thing where, like, you can we read about this at one point, but I forgot what it meant. I don't use it. Other than assert. Assert is useful, I will say that. Assert basically is a way of checking if something is true. And if it's not true, then it throws an exception. Kind of, in most cases. So, like, for example, let's see. If we have this function here, which is called int, or, so they have contract where it's like in and out. But let's say we had like an assert statement, and it's like compare B to 10, and if B doesn't, or if B is less than 10, right? So B is 10. Obviously, it's not less than 10, and then it will return false. And if it returns false, then it throws an exception at that line. I mean, I could do an example of that, but I don't really need to. I think it's pretty obvious what it does. It's just a way of checking things and then throwing an exception. So that way your program doesn't have some weird shit going on. It's a stability thing. But in and out blocks is interesting. I haven't read about this yet. Let's go ahead and review this, I guess. Contract programming is a software design approach that treats parts of software as individual entities that provide services to each other. This approach realizes that software can work according to its specification as long as the provider and the consumer of the service both obey the contract. So that's kind of confusing, but these contract programming features involve functions and units of software. Services like in unit testing, which is important. Contract programming is also based on assert checks. So yeah, what we just saw. So is that like just an if statement basically? In blocks for preconditions, correct execution of functions is usually dependent on whether the values of their parameters are valid. For example, a square root function may require that its parameter cannot be negative. So then you would do that, where you assert for less than zeros and shit. In contract programming, the same checks are written inside the in blocks of functions. So I guess that's just a cleaner way of writing that. When an in or out block is used, the actual body of the function must be specified as a do block. Oh. Okay. So in, and then it does that. So it takes an in of that, and then it's like, oh, assert hour that it does not do this, is not greater than or equal to 0, and hour is not less than or greater or less than or equal to 30, bro, less than or greater less than or equal to 23, and then semicolon, and then assert minute. So in this case, they have those two asserts which check the hour and the minute to make sure that they're valid, and then if they are, return the format for the hour and the minute. And then after that, there's void main, which does write line time to string 12 and 34. And that returns a format, by the way, or formatted right, I guess. So that's pretty interesting. So a format is a struct that probably contains a string or something like that. The body keyword was used for this purpose instead of do. So this is what in earlier versions of D. Okay. Out blocks for, like, I like that they use do for that. Out blocks for post conditions. The other side of the contract involves guarantees that the function provides such, so like, for example, the function itself, right? The stuff in this do is going to return a result, right? Or, yeah, oh, wait, out is a result. Return is leap year. Maybe. Or, so if result is 28, or result is 29, and that's a ternary operator there. So it's doing a year 29 or 28. But if it, well, if one is true, then the other's not true. But I'm kind of interested. What is this? Why is hold on, let's go back. There's a function that provides the such guarantees are called the post conditions. Another example of a function with post condition would be a function that guarantees the number of days in February. The function can guarantee that the return value would always be either 28 or 29. So, like, what is contract programming really like? I mean, I get it as for functions and shit. So in is optional, out is optional, but do is mandatory. So if you have one or the other, you need to have do. But you don't need do if you don't got any of them. So I mean, I think there's an advantage to not having to put do in my code, bro. Mountain Dew. Other valid names may also be used. Some functions do not have return values. Okay. Okay. Anyway, next. Fundamental operations. Wait, this is in lifetimes. Lifetime of a parameter. Just an alias of an actual variable that is specified. Finalization and assignment. Oh. 3. For the lifetime of a variable, it goes initialization, finalization, and assignment. So that'd be changing it. Oh, so there's like finalization, like kind of like making it immutable almost, but like not really immutable. Reserving the space for the variable. Right, so like, yeah, that makes sense because, I mean, you can't really just create a variable on an operating system without having it, like... You see, the operating system handles all that shit, like memory and stuff like that, but it's also part of the programmer writing the code who has to allocate memory to an extent. It's kind of like both. Like, the operating system, I think, tells it where to go, and then the programmer kind of allocates memory to it, and then if it exceeds a certain limit, then the operating system can throw an exception to, like, kind of not have the thing run, because then it would be exceeding the memory limit or something like that. Or, I'm not sure exactly. I feel like that's beyond my expertise at this time. I'm just speculating. Reserving, so yeah, of course you reserve space for the variable. Like, as I discussed, here, let me pull up an example of my own code that uses this. dtools should be in socket, which we were working on this, but we didn't really get very far. Socket. I don't know why that's that color, but maybe alt-click it. It's fucking colored for some reason. I don't know. But anyway, you can see here, new byte basically assigns. Also, this is LAN that connects to a gigabit Ethernet switch, so don't even worry about that. It's 100% safe for me. Oh, here we go. This is the ubyte buffer, which allocates 1024 length to a dynamic array called buffer. So dynamic array can be up to 1024 long. Well, technically, it is 1024 long. It just allocated to that. Now, then in the right line, this is overwritten. So it would be allocated as zeros here, but it's overwritten. So, for example, I should have actually another one where I rewrote it. Let's see. Because I don't have to recompile it, but I should have one inside of a... What was it called? Like more code or something? I actually might have gotten rid of that. More code. Oh, there is something in here. Never mind. That's literally what this is. Okay. Well, yeah, I had one that was a local host one, and I can demonstrate what it does, is it just literally just pulls up all the information about your browser and stuff. That if you connect your browser to it, which you can connect your browser to it. It's crazy. Because I didn't expect it to be able to do that. Apparently you can connect a browser to such a thing, but I don't know how to... I'm pretty sure you actually have to serialize the data and then send it over as packets. And also, before you send it, obviously, zip it up, like, compress it. But not using zip, like zlib. Use a zlib or something like that. There's a way to do it. And then compression, obviously, is super important. Compression is like the most important algorithm, honestly. Everything needs that nowadays. My RAM, my computer. Obviously, my computer needs that. So, like, let's take an array and try to get bits from the array. Anyway, what do I want to do? Oh wait, we're still reading. Back to reading. Let's get focused on reading, because that's what we should be doing. Construction, setting the first value of the variable on that space, or the first values of member classes, of structs and classes. Obviously, a struct and a class are going to take up more memory space, so we should be interested about that. Obviously, memory location is called its address. So, like, yes, in like binary, like the address is what is it called? Or no, not in binary. In assembly, address is important because it is stored on a register or your RAM, which, I mean, I think you can do RAM stuff with assembly. I don't know how to do assembly, guys. I'm a fucking noob at assembly. My last time touching assembly was like a couple months ago, so... And I was touching ARM assembly. Prepare variables for use, since a variable cannot be readily or reliably used before constructed. It is performed by the compiler automatically. Variables can be constructed in 3 ways: by their default value, when the programmer does not specify value explicitly, a bunch of other stuff. Keep scrolling down. So destruction, the final operations, and reclaiming the memory. So it's like in the opposite order. So first it allocates memory, then it constructs it, and then does stuff with it, then deconstruct and reclaim. So opposite order. It's pretty simple. That's like how everything should be. You go do something, it should be done one way, and then if you have to, then you have to redo it in the reverse order. Finalization. So I think the way we could really use this better is by specifying the scope. I'm pretty sure scope allows you to get rid of variables, because the second a scope closes, that's what handles a lot of that. The null value and the is operator. Oh, segmentation fault. I love SigSev, bro. SigSev is awesome. Oh, SigSev V. Zigzag V. Next. 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 Or wait, did we already reach the construction one? Bro, what page am I on? Oh, my search is on that. Oh, never mind. Oops. I went too far. I think we might have passed it. Or no, we're good. Constructor and other special. Oh, right. These are familiar to me. Oh, that's for deconstruction. Oh. Give some examples. Please give me some examples. So, for example, we have a variable or immutable a. Oh, wait. Constructor syntax? So you got like an S for before immutable. So he has like immutable S and then 2. More familiar syntax, immutable version of a mutable type. Oh, what? Very interesting. But yeah, the way we could actually do it more efficiently is user sign. We describe the behavior of compiler-generated constructors. Since a constructor is suitable for most cases, there's no need to define a constructor or constructor by hand. Still, there are cases when constructing an object involves more complicated operations than assigning values to each member in order. As an example, let's consider a duration from the earlier chapters. The compiler-generated constructor is sufficient for this single member struct. Since that constructor takes the duration in minutes, the programmers would sometimes need to make calculations. To eliminate the need for these calculations, we can design a duration constructor. Right, so like a function that goes in there or something. Oh, never mind. This int hour, int minute. That makes sense. Yeah, that makes sense. Int hour, int minute. Construction. Ugh. Whoa. It disables compiler generated constructor. I mean, yeah, obviously would do that. Oh. Wait, there's another thing with this. Constructors for like, when you look at, what was it? That one code I had, the socket code. It has its own constructors built into the standard.socket. That thing had its own constructors as well. Constructed with constructor, deconstructor, constructor. I'm pretty sure we just need to put in scopes to make this efficient. Like, to make this as efficient as possible, and then not waste up extra memory resources. You would just declare these inside of a scope. It's just that simple. And then, you could also call destroy if you wanted to get rid of it in the middle of the scope, but I don't think you need to do that. I think that's only really for classes, too. So that's fine. Let's make this more memory efficient. The void main, at least. We'll just do a write line for now. So that makes it the most efficient we can get it. And then Alright, so now we need to make a set bit. Technically, we can do a get bit array, and we can rebuild that. So we'll start off with the easiest option, which is to create a set bit array. Or copy that. Boom. Just copy and paste it. It's pretty much going to be the same shit. So instead, we're going to do a ubyte input. And then we're going to do none of this. And we're going to return an output. Oh. Well, all you would do is then... But we want to take this set bit array, and we're going to make it into another way of making a string of bits. Or no, like a bunch of bits. Or something. But we need to use a ternary operator for this. Let's make the set bit first. Set bit's probably easier. So working with int, obviously we'll do int set bit. Start off easy and cheesy. We'll also do a write ln. Oh shit! Never mind to do that. Input right here, and then comma. Wait, write ln. What the fuck am I doing? Just put input right there. There we go. Oh man, it would be so great if I had a function that just did this for me. Just create a function for that, bro. I mean, hell, if you use a lot, you could just make a function of anything. Alright, let's continue. I actually don't really know where to start with that, per se. All right. Let's create a. Let's just go. Oh, I'm gonna keep this. Throw that in the other browser window. Alright, what we really need is to now ask the real hard question. What? Oh. What? No. No, we don't need slang. Set bit delang. You can set bits using standard bitwise operators or the standard.bitmap benip and core.bit op libraries. Oh, what do they even provide you with in those anyway? I didn't even think to check those. I mean, we want to play around. We want to learn. We want to learn the bitwise stuff so we can have fun with it. Standard.bitmanip and bitop. Bitmanip. Yes. Please tell me about the bit manipulation. Super good, right? It has bit array, bit fields, bit set. Endian conversion, integral ranges, Can I write a bit? What does that do? Oh, you write endianness? Oh god. That's like so complex for something I don't really need to do right now. Alright, well here for direct manipulation, use the Bitwise OR operator with a mask, which is like I was speculating, it is the opposite of what we did earlier. So, for example, well, actually, I don't need an example. Example is Exhibit A. But, what is this? So the bit position, and then 1, and then the mask. So, like, wouldn't that be the value? Let's use bitwise operators. But yeah, it's basically the same thing I did earlier, where it's got a mask in there. Use the bitwise OR combined with a left shift. So it's the opposite this time. Instead of an AND, it's an OR. Instead of a right shift, it's a left shift. To set the bit at position N, where the 0 is the least significant bit, desired value, where only the nth bit set to 1 performs a bitwise OR, turning the target bit to 1, leaving all other bits unchanged. And then there's one for setting multiple bits. Oh, so this is good stuff.
Thank you, Mr. AI Robot Man. You've told me such good things today.
But yes, you can technically do that. So would it be like output equals output O? So no, you would do... Alright, so for set bit, we'd take an int input. Input? What the hell? Am I turning French or something? Oh god. Take an int input, and then you're going to do the input pipe equals, right? Pipe equals to the other thing, which is of course an OR. 1, and then OR for position, comma, int position, and then you return input. Boom. We should also follow the same principles that this follows, where we cast it to a ubyte. So it outputs a ubyte from an int. Since we don't really want to mess around too much with well, no, because then you could throw in some fucking huge-ass number and fuck it up. Wouldn't it make sense to just do this using ubytes and then split up, Why would I do this? I think it's a dumb idea to put the cast there, even though it would make it iterate cast less times. We saw in the testing that it didn't really matter if it iterates cast a bunch of times. I mean, it's gonna do it anyway. Might as well be smart about it. Keep it simple, and just keep the cast here. So that will allow us to get our set bit. So then when we do a set bit on, we'll put the set bit here. So we'll do get bit array for the set bit set bit. Actually, yeah, output, and then set bit with a. Also, there's some interesting stuff with the what are they called? Parallelism stuff, threading and stuff. There's some interesting things I never really thought of before, but every time you create a new thread and stuff like that, or create a new task or stuff like that, the memory is an interesting thing that we should take note of, is that if you create one that uses like the same, let's say you create a bunch of threads that all share one value, right? And they all do the same thing to it. That's pretty much useless. I mean, I think anybody would have came to that conclusion, but I just came to that conclusion right now, and I was like, that's pretty useless, and it probably just wastes a bunch of fucking memory for no reason. But I was thinking we could technically use parallelism to parallelize the task of setting bits. Instead of doing it using one bit at a time, we could technically try to do that. Or, theoretically, we could just take a bunch of these bits and assemble them using that same principle. Or, well, actually, it just makes sense to literally all you have to do to make that happen is append these to a... No. You wouldn't append them to an array. Well, could you? Well, I mean, you could technically store 4 of them together, and then add the values of 4 of them, and I think you could be fine. I don't know. There's a bunch of stuff to think about for later. So we'll take input, input, like I said earlier, whatever the hell that is, 0x0. 0 would be the first value, and we want to set that to, well, it says it sets it to 1. However, technically, you could just say the value to set to, or actually just put 2. That way it's easier to read. 2 is way easier. Or input. What the fuck? Bro, you can tell I'm tired. Control S. And so we can then do a 2, and we want to set it to like, it can either be 1 or 0, so you only really have 2 options. 0x0, 1, or 0. And if you set it to 1, then, I mean, technically, no, don't worry about that. We could have just done an input there instead of declaring a whole new variable. But, input, output, comma, this, space, comma, output. Should give us what we're looking for. So then we'll DMD. And the expected result was that it would set one of them to 0, x 0. As we saw, it did not do that. Instead, however, it did... Wait, it gave us 15, 15. What number did I say? 0x0? 0x0, 1. That first one's the position, right? Not the value we're setting it to. Not exactly. Something's weird. 0x0. And set it to 1. Actually, what if input's wrong? What if that's wrong? Well, I mean, input should be input. But 2 in position should be different, right? 0x0, 1. Well, we tried that. We set it to 1 earlier. I mean, like, what does that get you? Like, it's setting... Well, I guess the mask is the shift 1 position right. So that should just be a static, right? I think that should be static. What if they're both 1? What happens then? Shift the integer at position 1 left by 1. And that gives us nothing. Wait. Maybe we do 0x05? Because technically that is the position. Oh, wait. 4. Try 4, bro. Never mind. Alright, well I think I'm gonna wrap it up here. We've done a lot today. This is a lot more than we've gotten done in the past 4 episodes. I mean, we've written how many functions? 2 functions that are completed. I believe they're completed, unless correct me if I'm wrong, but these are completely functional functions. They work well, questionably well. Although we still need to work on this last one, but that can be done later. I actually think what's going on here is probably like some kind of overriding of the original input value, even though this is a that. We might need to just take a value of the original and put it into a different variable, and then, but we can figure that out between episodes. And yeah, it's been pretty productive. So I'd like to thank you all for watching. I'll see you all in the next one, when hopefully we'll continue working on my Bitwise operations. And see you all then.